Assalamualaikum warahmatullahi wabarakatuh and good morning. So we continue our discussion about boat plot based on the previous lecture about how to draw the boat magnitude and phase magnitude. Let us look at this simple example with GS equal to 100 divided by S plus 30, and this is a first order system. So in order to plot this both magnitude and phase plot, so first we have to change this S with J omega, and then we have to make sure this part should be equal to 1. So in order to change this part equal to 1, so we have to multiply this denominator with 30. Where when we time with 30, in order to maintain the same equation, so we have to put 30 here, and this one become 1. Based from this result, so we know that the cutoff frequency for this equation is at 30, which is considered as a low frequency when the magnitude plot start change 20 dB per decade. So in this case, decrease negative 20 dB per decade because this j omega is at denominator part. And based on this equation, also can calculate this k here. So in this case, k is equal to 3.3. So based on this value of k, so we can calculate the magnitude for this gain is equal to 20 log 3.3, which is equal to 10.4 dB. So after we get this magnitude and also this cutoff frequency, and then we can combine both to draw the both magnitude. And also for this phase plot, so based on these equations, when k is equal to 3.3, and that's mean in this equation, the component for j omega is equal to 0. And that's why phase plot for gain is equal to inverse tangent 0, and because this imaginary part equal to 0, so that we just put 0 here divided by 3.3. So when 0 divided by any value, so we got this one equal to 0. Inverse tangent 0 is equal to 0 degree per decade. So based on this cutoff frequency at equal to 30, so we just draw the both magnitude like this. Start with 0 dB till this point, which is at 30 radian per second, and this one is 10 power of 1 equal to 10, and this one 10 power of 0, which is equal to 1, and this one is equal to 0.11. So you can start from 1, or you can start from 0.1, or you can start from 0.01. It's up to you, as long as this cutoff frequency is covered in this both diagram. So in this case, this cutoff frequency is at 30 radian per second, and after meet this point, so this magnitude decrease 20 dB per decade because this component is at denominator part. So based on this cutoff frequency, lower cutoff frequency for phase occurs 1 decade before this 30 radian per second and end at 1 decade after this 30 radian per second. And that's why, as you can see in this plot, the cutoff for the lower frequency is at this part, which is equal to 3, will decrease that from this lower cutoff frequency with negative 45 degree per decade. This space block will keep decrease till meet this high cutoff frequency, which is equal to 300 radian per second, and where this 300 is 1 decade after this 30 radian per second. Now let us look at another example. Draw the both magnitude and phase plot for the transfer function below, where GS equal to 10 divided by S plus 2 times S plus 4. We use the same procedure. First, we have to change this S with J omega and just change like this. And then after that, we have to make sure this part and also this part should be equal to 1. So in order to make it this part equal to 1 and also this one equal to 1, so we just multiply this equation, this one, with 2. So when we put 2 outside here, so this equation become 2 times j omega divided by 2 plus 1. And also for this one, if we want to make this part is equal to 1, so we just multiply this part with 40. So when we multiply with 40, so this equation become j omega divided by 40, and because when we times this with this, we get again the value for j omega only. And then when we time 1 this with this 40, so we get again this equation j omega plus 40. So from here, we can rearrange this equation like this, where this value at 20 40, so we combine together with this value 10 here. So this become value of k, where k in this case is equal to 10 divided by 80. So based on this transfer function in frequency domain, so in order to draw the dot plot, the cutoff frequency is at 2 radian per second and 40 radian per second. To start plot this board diagram, so first we have to find the magnitude with respect to this gain, where in this case k equal to 10 over 80, which is we can simplify become 1 over 8. We just use the same formula we have used before, which is 20 log 1 over 8 here. So after we calculate, so we get this equal to negative 18.06 dB. So that's mean for gain, the magnitude plot will start at negative 18.06 like this. So for this case, for this k equal to 1 over 8, the component for j omega is 0. This is the same like I have mentioned before. So that means phase plot for this k, for this constant value is equal to 0 degree. So that means for phase plot, we just draw a horizontal line at 0 degree like this. For the next component, which is the component we refer to this, so we can simplify like this. J omega equal to 1 over j omega divided by 2 plus 1. Okay, from this, so we know that the lower cutoff frequency is at 2 when omega is equal to 0. So that means the cutoff frequency is equal to 2 when the lower cutoff frequency is equal to 2. So from this information, so we can draw the magnitude plot like this. We start from 0 dB, and then at this 2 radian per second, this plot will decrease because this component is at denominator. So this one will decrease negative 20 dB per decade. So for the phase plot, the starting point or the lower frequency that the phase plot start change is at 2 divided by 10, which is 1 decade before this cutoff frequency. So we get this one is we get the value for this lower cutoff frequency for phase plot is at 0.2 and end at 20, because which is 1 decade after cutoff frequency. And then the slope should be negative 40 degree per decade, based on calculation by using inverse tangent component for this imaginary divided by component for this real part, because this component at denominator, so the equation become negative inverse tangent omega over 2 divided by 1. Okay, next, for this second component here, the same procedure we use as this component, and only the change, only the difference is the cutoff frequency. Where in this component, the cutoff frequency is at 40 dB. So that's mean at 40 dB here, the magnitude plot will start decrease negative 20 dB per decade. And also for this phase plot, uh, because of this one is equal to 40, so this phase plot start change at 40 divided by 10 equal to 4 and end at 400, and because this 40 time with 10, and then maintain at negative 90 degree because this component is at this denominator part. Now, after we get all this drawing for this magnitude plot and phase plot for each component of the transfer function, so we can combine to draw the overall board plot by using semi-log graph. So in order to combine all this, so first we have to draw the plot based on each component. So for component of gain k, where the magnitude is at negative 18.0.6, so we just draw this dot line here, which is at negative 18.06. Okay, for this component, where the cutoff frequency is at 2 radian per second, so we just draw a line start from this 0 dB till this cutoff frequency, which is at 2 radian per second, and then after that, we just draw the line which is negative 20 dB per decade, like this. And also for the next component, and this one for the cutoff frequency at 40 radian per second, so we just draw the same line like this till 40 radian per second, and after we meet this 40 radian per second, we just draw this line which is parallel with this, that is represent negative 20 dB per decade. And after we draw all these three lines here and based on these transfer functions, so we can combine all together. So where the starting point for this board plot should be at 0 minus 0 plus 0, because we have two line here, line for this one and line for this one. So that's mean 0 plus 0 minus 18.06, and we refer to this horizontal line here as a component for gain at this point. So after we combine, so we get the starting point for this work plot should be at negative 18.06, and that's why we start the work plot from this point. Okay, and then at cutoff frequency 2 radian per second, only one slope here, so we just draw the line that is parallel to this slope, which is equal to negative 20 dB per decade, until the next cutoff point, which is at 40 radian per second. Okay, at this point we have two slope here. This one represent negative 20 dB per decade, and also this one represent negative 20 dB per decade. Okay, negative 20 dB per decade plus negative 20 dB per decade become negative 40 dB per decade. That's why this line become like this, and because this slope become negative 40 dB per decade. And then after this cutoff frequency, there is no other cutoff frequency, so we just draw straight line till end. Okay, this is the overall both magnitude for this system. So we can see here the starting point is at negative 18.06, and then at first cutoff frequency, this plot decrease 20 dB per decade till 40 radian per second. And at this 40 radian per second, because we have two components with the same slope here, and negative 20 and negative 20, so we just add this together, and then the slope become negative 40 dB per decade. Okay, next for phase plot, it can also be handled similarly, where the phase plot is having a slope of negative 45 degree per decade, which is occurs at 0.2 radian per second here to around 4 radian per second here, where the slope will then increase negative 90 degree per decade at this 4 radian per second to 20 radian per second, and then after this 20 radian per second, it will then return to negative 45 degree per decade, and like this from this point till 400 radian per second, and finally from 400 radian per second to infinity, the slope is remain 0 degree per decade. The increasing of this slope because of the combination of these two slope, which is negative 45 degree per decade plus with this negative 45 degree per decade, which is equal to negative 90 degree per decade. Okay, the changes for this slope because of one of the slope is already settled at this 20 radian per second. So start from this point to this point, only one slope which is equal to negative 45 degree per decade, and that's why this slope become negative 45 degree per decade. And then starting from this point, so there is no slope. So that's why this phase plot remain at 0 degree per decade. Okay, you also can plot this work plot by using MATLAB. Just follow this step and then just type both in bracket G. G is equal to this transfer function, and then you will be directly get the result for both magnitude and place after you click enter. So now let us look at what happened for the system with the second order term. So the second order polynomial can be represented as a following equation. And let's say if we have only a numerator like this, s square plus s theta omega ns plus omega n square. So we can rearrange this equation become like this, and we just put this omega n outside this bracket. So the equation become omega n square times s square over omega n square plus 2 zeta s divided by omega n plus 1. And why we need to change this form until we get this form? Because we want to make sure this component should be equal to 1, which is same like previous explanation about the first order system, where this component should be equal to 1. So before we can plot this both magnitude and phase, first we have to change this as with j omega. So after we change this as with j omega, this equation become like this. So for low frequency, which is occurs when this omega equal to 0, so we just put this omega equal to 0. So this component becomes 0, and also this component become 0. So this equation become gs equal to omega n square. Okay, for phase, the real component, because of this one is equal to 0 and this one is equal to 1, and the imaginary component is equal to 0 because this one is equal to 0. So from equation, inverse tangent imaginary component divided by real component, in which this imaginary component is equal to 0 divided by 1. So the result for the phase is also equal to 0 degree. That's why we get at low frequency, this equation become omega n square with a phase equal to 0. So therefore magnitude m in dB, for this case we can use the same formula. So 20 log m. In this case we just put m with this j omega. So j omega here is equal to omega n square. So we just put 20 log omega n square. Okay, meanwhile at high frequency, this equation become s square because when we put this omega equal to infinity, and this component become negative infinity, and also this component become infinity. So when this component become infinity at times 2, so this component we can ignore. That's why the result become s power 2 or j omega power 2 or omega square with angle 180 degree. In order to calculate this phase, we just use the same formula as previously mentioned. So after we use that formula, so we get the phase is equal to 180 degree. So therefore magnitude m in dB at this frequency is 20 log m, which is 20 log gg omega, in this case equal to omega square. So we just put omega square here. So because this is log, so when omega square, so we can put this square uh, in front of this log, so the equation become 40 log omega. According to these equations, the asymptotic approximation of second order system can be drawn as a straight line with twice of slope of a first order system, or 40 dB per decade for magnitude and 90 degree per decade for phase, as shown in this figure. So the cutoff frequency is occurs at omega n, where the cutoff frequency for this phase plot, the breakpoint or cutoff frequency is occurs 1 decade before and at 1 decade after omega n. So for a second order under them, so there are several characteristics that should be taken into account while we draw this word plot. So first, low frequency asymptote, which is occurs when omega is equal to 0. Next, breakpoint at omega equal to omega n. And Next, high frequency asymptote, which is equal to negative or positive 40 dB per decade, and depends on either the component is referred to numerator or denominator. Resonant peak is at high 1 over 2 zeta, and the actual maximum occurs at omega equal to omega n times with set for 1 minus 2 zeta square. So this is for magnitude response, and for phase response. So low frequency asymptote is at 0 degree. Break point with 90 degree that occurs at omega equal to A, or 1 decade before omega n. High frequency asymptote is negative or positive 180 degree, depend either the component is referred to numerator or denominator. And central slope cross 0 dB at omega equal to omega over 5 theta, where negative 80 degree at omega equal to 5 zeta omega n. So according to this characteristic, the magnitude plot for second order system can be drawn like this. The drawing start at 0 dB, and the cutoff frequency is at omega n, and the slope start from this cutoff frequency is equal to negative 40 dB per decade. This is the equation that represent the magnitude for this plot. So when the case omega is less, very less compared to omega n, so the result becomes 0 dB like this. And when omega is greater or very big compared to omega n, so the equation become negative 20 log omega square, so which is equal to negative 40 log omega, and like I mentioned before. So this is the exact board plot that we can draw, where this curve is depends on the value of zeta, which is referred to this formula where hj omega n equal to 1 over 2 zeta. So from here, so in dB we can change to negative 20 log 2 zeta. So the exact corner frequency for this board plot can be obtained by apply this formula, which is depend on the value of zeta starting from 0 to 1. So the correction may be above the asymptote, which is positive, or below, which is negative, depending on the value of damping factor or damping ratio. The difference between the actual response and the asymptotic approximation of the second order system is greater if compared to the first order system. So the first order system has a gap about 3.01 dB magnitude and 5.71 degree of phase, but for second order system it gap is varies depend on the value of theta. Next, from magnitude plot and phase plot, we can check the stability of the system by obtain the gain margin and phase margin. So the gain margin is found by using the phase plot to find the frequency omega gm. Frequency omega gm means omega gain margin, where the phase angle is at 180 or negative 180, depends on either that component is referred to numerator or denominator. So at this frequency, we look at the magnitude plot to determine the gain margin AGM, which is the gain required to rise the magnitude curve to 0 dB. While for phase margin is found by using the magnitude curve to find the frequency omega Vm, where the gain is equal to 0 dB. On the phase curve at that frequency, the phase margin Vm is the difference between the phase value and 180 degree or negative 150 degree, depend either that component is the numerator or the numerator. So for the system with damping ratio, where there is involved with zeta, so the phase margin also can be calculated using the following formula, which is Pm equal to inverse tangent to zeta divided by sed negative 2 zeta square plus sed 1 plus 4 times zeta power of 4 And from this gain margin and phase margin, so we can know the stability of the system based on the value of GM. So if the GM is negative value, so the system is considered unstable. While when the GM is positive value, the system is stable. So in the case of omega GM and omega VM is equal, so the system become marginally stable. Okay, that's all for today. So hope you can understand, and if you still have a problem, don't hesitate to contact me through WhatsApp and we can discuss. Assalamualaikum warahmatullahi wabarakatuh. Thank you.